Now next is, that is, we have learned which is dextran, which is levo, and theoretically how do we find it out whether the compound is optically active or not. Now if the compound is optically active, we are having two types of optically active compounds. What is that? One is enantiomers, another is diastereomers. What I said you? One is enantiomers and another is diastereomers. Enantiomers means when the mirror image of the compound is not superimposable. Alright, when the means of course they are not superimposable. Of course you can see it here, both are. But when this particular compound has got a mirror image, this compound has got a mirror image. But when this compound does not have a mirror image, that is said to be as diastereomers. In both the case, the mirror image is not superimposable. That's true. But here we have got a mirror image and here we do not have a mirror image. More of it you can see in my notes I have given to you in class 11 when I was teaching you. In that I have given you the difference between enantiomers and diastereomers. I have given to you and I have told you a lot about it. But still in here I will say you now how it is mirror image and how we don't have a mirror image. Let us take an example. Here. Like let us take here CH3, here let us take Cl, here let us take Br, here let us take H, here OH, and here it is CH3. Yeah, you can say CH3 or you can say C2H5. So as you can see, these two are chiral carbon atom attached to 4 different atoms or groups. Now I am going to take the image of it. So what I will get it here? I will get Br and I will get Cl here. And here it is CH3. Here same thing, I will get OH and here it is H and here I will get C2H5. Alright, so this one, second one. So you can see this is a mirror image of this. As you can see, this is a mirror image. Don't forget to put the asterisk mark. Alright, so it is having a mirror image. What I said in enantiomers, they have got a mirror image. Now I am putting it another one. The next one I am drawing it. Let us say I am doing it here COH, here it is Cl, here it is Br, and here it is or let me put it here I, and here it is C, and here it is let me put it here Cl. I don't have the space here unfortunately. Here OH and here it is CH3. Okay, so this is third one. So what you find is that now of course we'll have a mirror image of this also. We'll have a mirror image of this. The fourth one will have it, but I don't have the space. You can write and see. What you have to do is that just have to change the right and the left, you have to change it. OH will come here and Cl will come here. That's it in the mirror image. So what you see is that 1 is the mirror image of 2. Listen carefully. 1 is the mirror image of 2. Is 2 the mirror image of 3? Is 2 the mirror image of 3? No. Is 1 the mirror image of 3? No. So 1 and 2 are enantiomers. 2 and 3 are diastereomers. 1 and 3 are diastereomers. Suppose you will be having another one, 4. You do it and see in your home. They are also known as what? Diastereomers. I think you got it now. What are enantiomers and diastereomers? Enantiomers, they have got a mirror image of itself. But diastereomers does not. We can see that. Okay. So these two are optically active, what you can say, compounds. So what I said you, optically active isomers are of two types. Enantiomers and diastereomers. Fine. Now next is, after that we are having, that is, optically inactive compounds are also two types. What is that? Mesocompounds and racemic mixture. Mesocompound. Mesocompound means when the compound is optically inactive due to internal compensation. When a compound is optically inactive due to internal compensation. What do you mean by internal compensation? The internal arrangement of the compound is such that it is 50% dextro and 50% levo. Means half of the compound rotates towards right and the other half rotates towards left. The net rotation will be what? 0. Hence the compound is said to be optically inactive in nature. So what is that I said to you? Internal compensation. The internal arrangement is such that. Got it? So here in this case we are having a plane of symmetry. We are having it. How? I'll show you an example. Here HOH, here let us say, here we are having OH, here H, and here we are having CH3. So you can say this is a plane of symmetry. This overlaps upon this. This is a plane of symmetry. This line is a plane of symmetry. Dotted line which I have drawn it here. This is a plane of symmetry. So this compound is said to be mesocompound. The internal arrangement is such that it is optically inactive due to internal compensation, 50% dextro and 50% levo. Now coming to racemic mixture, what is that? For that purpose I have to tell you a little bit more. Now racemic mixture is optically inactive due to external compensation. External compensation means externally you are adding 50% dextro compound and 50% levo compound, means you are taking 50% dextro and 50% levo. So the net rotation is what? 0. So meso compound is optically inactive due to internal compensation. Racemic mixture is optically inactive due to external compensation, and the phenomena is known as racemization. It is known as racemization. Achha. Here one more term you will be getting in your book, resolution. Resolution means what? That is, it's a process by which you separate the dextro and the levo compound. That's known as resolution. Means you are having dextro and levo compound, a mixture you are having it, and the process which you are adapting it to separate the dextro and the levo compound, that is known as resolution. That is said to be as. Alright, for that reason I said it cannot be resolved. You might have heard the word it cannot be resolved. I have used the word resolved. Means it cannot be separated into dextro and levo. In which case? In case of meso and in case of racemic I said you. Okay, they are optically inactive in nature. Now next is, what we find is that when you are expressing an optically active compound, so we have got two types of expression that also I have discussed. One is the Fischer projections. Fischer projections is that, for example, you are having a lactic acid in this way. Let us say you are having, this is your lactic acid, this is your chiral carbon atom. So here in case of Fischer projections we do it in this way. We don't represent the central carbon atom, we write it as CH3, here it is H, here it is OH, and here it is COOH. So this is your Fischer projection. This is a type of representation of an optically active compound. Another is your three-dimensional structure. Three-dimensional. In three-dimensional structure, what we do is that we draw, that is CH3 in this way, let us say, and here H we are drawing this way, and let us say we are having a dash. Dash means this sort of a line we are having, this is known as a dash. This is OH, and we are having a wedge. Wedge means this is a dark line, that is COOH. What does it mean? That means these two groups are on the plane of paper. What I said is this is three-dimensional representation. This is said to be as three-dimensional. These two are on the plane of paper. Now here the dash, that is we can see is that it is nothing but it is inside the plane of paper, inside, and this is outside, away from you. What it? COH, it is dark one is away from you. This is on the plane of paper, this is inside. OH group is three-dimensional represented, three-dimensional representation, not two-dimensional. Okay, and this particular one is nothing but it is away from you, away from this, upward it is. Got it? This is. So this is Fischer projection, this is three-dimensional, what you can say, representation, and this is your, of course, two-dimensional representation. Okay. Now here we will be coming here to it. That is, one is your retention, another is your inversion. I have talked to you about inversion, about Walden inversion, if you remember it. In SN2, what you can say, this substitution nucleophilic reaction I have talked with you. That is SN2 reactions, that is Walden inversion. So that I am going to show you. The first I am going to tell you about retention. Retention means when the stereoisomeric form is being retained after the chemical reaction is taken place. Stereoisomeric form means whatever the representation was there of the reactant, after the reaction has taken place, the product which is formed, it has got the same representation in three-dimensional structure. The representation does not change. That means that is left and right, whatever the group is there, it does not change. It remains as it is. Alright, now let me give you an example, then only it will be clear to you. Let us say this is C2H5, this is H, this is nothing but CH2Cl, and this is your COOH, let us say. Alright, now it reacts with HOH. It reacts with HOH. When it reacts with HOH, what is going to form is that HCl is released, and instead of that, you are having this. An example I am giving you. This reaction, just an example. And this is your nothing but CH2OH, and this is your COH. So what you find is that Cl, it is retaining on the same side, OH is retaining, it's replacing Cl and it's retaining on the same side. OH is replacing Cl and it's retaining on the same side. What I am saying? Retaining on the same side. So hence what I said you, this is nothing but retention. But suppose in inversion what will happen? This OH will come this side. Got it? Then what is that? That phenomenon is known as inversion. Again I repeat, the reaction will take place in such a manner that OH will be coming this side, means CH2OH will be this side and H will be on the other side. Then what is that known as? Inversion. This is known as what? Retention. Retention. Listen carefully. OH is on the same side as that of Cl. I have retained OH on the same side. So this phenomenon is called as retention. That is known as. But suppose CH2OH is on this side and H is on the opposite side, this other side. Means left and right it changes. Then what I said it is inversion. Where you have understood inversion? In SN2 mechanism you have understood inversion. That how the inversion reaction is taking place. I said you the Walden inversion. Now let us say this is your A, retention, the product which you got it. And for this inversion, let us say this is the product you will be getting it. That is CH2H on this side and H on this side, and this is your COH. This is your B. Let us say A plus B together is known as what? Racemic mixture. This is called as racemic mixture. This one is, and the phenomena is known as racemization. What I said you, this is retention, this one is inversion, and when I combine A and B equally and mix it, I get an optically inactive compound. What is that known as? Racemic mixture, and the phenomena is known as what? Racemization. It is said to be. So retention, inversion, racemization. I hope it has been clear to you. This is about your optical isomerism. Thank you.